we are going to study some standard probability distributions. Out of them, first two are binomial distribution and Poisson distribution, which are discrete in nature, while the third, normal distribution, is continuous in nature. In this video, we are going to focus our attention on the binomial distribution. Hello friends, you are watching YouTube channel Number Collage. This channel features videos on mathematical concepts. Effort has been made to explore the concepts through basic mathematical ideas. Hope you will like my effort. In binomial distribution, word binomial itself suggests that it deals with the events resulting in two outcomes, success or failure. By success and failure, we mean yes or no, good or bad, head or tail, pass or fail, etc. If probability of success is P and that of failure is Q, then as we know, P plus Q is 1. Let an experiment is repeated n times and probability of success P is constant and probability of failure Q changes according to P, and since P plus Q is 1, Q will be 1 minus P. So in binomial distribution, we need to remember that the number of trials n and probability of success P, these two quantities are constant and they are referred to as parameters of binomial distribution. Suppose an experiment is repeated n number of times, and suppose P occurs x times, naturally Q will occur n minus x times. So by multiplication theorem, their probability will be P into P into P x times multiplied by Q into Q into Q n minus x times, which will be P raised to x into Q raised to n minus x. Now in n number of trials, x successes will occur in NCx ways. Hence, probability of x successes will be NCx P raised to x Q raised to n minus x, and hence binomial distribution for a random variable x will be NCx P raised to x Q raised to n minus x. Without going into the elaborate proofs of mean and variance, we will accept the results. Mean of binomial distribution is given by x bar or expectation Ex equals NP, which is a representative value of the set of probability distribution points, and variance is given by variance x NPQ, which measures how far each value of random variable x is from the mean and thus from every other value of the random variable. So we have to remember mean equals NP and variance equals NPQ. Tossing of a coin is related to binomial distribution because there are only two outcomes, heads or tail. Here there are three tosses, which means n is 3. Probability of h, say P, will be half, and that of tail, which is Q, will be 1 minus half, half. Mean is NP, 3 into half, 3 upon 2, 1 upon 5. Variance is NP into Q, 3 into half, 3 upon 4, 0.75. Mean is 1.5, which means we expect 1.5 heads in 3 tosses. Now let's write probability distribution of this problem. We have Px equals ncx p raised to x q raised to n minus x after putting the values 3cx p raised to x q raised to 3 minus x, where x is 0, 1, 2 and 3. Px equals 0 is 3c0 half raised to 0 half cube. 3c0 is 1, half raised to 0 is 1, half cube is 1 upon 8. Px equals 1 is 3c1 half raised to 1 half raised to 3 minus 1 2, which is 3c1 is 3 into half 1 upon 4, which is 3 upon 8. Similarly, px equals 2, so px2 is 3 upon 8 and px3 is 1 upon 8. We have to prove variance is maximum when p is half, which means that maximum value of variance is constant or fixed when probability of success is half or 50%. So, by the concept of maxima, derivative of variance with respect to p will be 0 because derivative of a constant function is 0. Now, variance is np into q, which is np, and q is 1 minus p, which is np minus np square. Now, derivative of variance with respect to p is 0. So, d by dp of np minus np square will be 0, which is n minus 2np equals 0, n into 1 minus 2p equals 0, which means n equals 0, which is not possible. Number of trials cannot be 0, which implies 1 minus 2p equals 0, p equals half. So it is proved that when p is half or the probability of success is 50%, variance is maximum. In previous problem, p is half and variance is 0.75. Now for any other value of p between 0 and 1, variance will be less than 0.75, which you can verify for yourself. In this question, mean, which is np, is 4 and variance, which is npq, is 3. We have to find binomial distribution px, ncx, p raised to x, q raised to n minus x. npq upon np will be 3 upon 4. Cancelling np, we will get q equals 3 upon 4 and p will be 1 minus q, that is 1 minus 3 upon 4, 4 minus 3, 1 upon 4. And finally, np is 4. So n into 1 upon 4 is 4. So n will be 4 into 4, 16. So we got p equals 1 upon 4, q equals 3 upon 4 and n 16. Now binomial distribution for a random variable x will be 16cx into 1 upon 4 raised to x into 3 upon 4 raised to 16 minus x. 60% of solar heat installations means P is 60%, which is 60 upon 100, 3 upon 5, which implies Q equals 1 minus P, 1 minus 3 upon 5, 2 upon 5. 4 of 5 installations means N is 5 and X is 4. This is a case of binomial distribution because the bill reduction will occur wherever there are solar heat installations, and bill reduction will not occur where there are no solar heat installations. So to find bill reduction in 4 of 5 installations, it will be P of x equals 4, which is 5c4 3 upon 5 raised to 4 into 2 upon 5 raised to 1. Now 5c4 is same as 5c, 5 minus 4, 1. 5c1 is 5, 3 raised to 4 upon 5 raised to 4 into 2 upon 5, which is 0.259. Now the second question, B, is probability of at least 4 of 5 installations that we have to find out. First, let us understand what is the meaning of at least 4 of 5. It means that probability of x greater than or equal to 4, and since n is 5, it will be p x equals 4 plus p x equals 5, which is 5c4 3 upon 5 raised to 4 2 upon 5 raised to 1 plus 5c5 3 upon 5 raised to 5 into 2 upon 5 raised to 0. 5c4 is 5 plus 5c5 is 1 into 2 upon 5 raised to 0 is 1. This 5 cancels with this 5, which is 3 upon 5 raised to 4 into 2 plus 3 upon 5 into 13 upon 5, which works out 0.337. So the probability that the bill reduction occurs in 4 of 5 installations is 0.259, and at least 4 of 5 installations is 0.337. It is given mean is 15 and standard deviation sigma is 5. Mean NP is 15. Variance is square of standard deviation sigma is 25. Here variance upon mean NPQ upon NP will be 25 upon 15, 5 upon 3. Cancelling NP, we get Q equals 5 upon 3, which is greater than 1. But Q being a probability cannot be greater than 1, which implies given statement is wrong. In another statement, mean is 12 and variance 3. Working in same manner, NPQ upon NP, 3 upon 12, 1 upon 4, which is less than 1, implies that given statement is right. So there is a fallacy in the first statement while the second statement is right. Here P is 1 upon 5, N is 6, Q is 1 minus P, 1 minus 1 upon 5, 4 upon 5. In the first question, we have to find probability that exactly 2 bombs will hit the target, which means P x equals 2. That will be 6c2 1 upon 5 square 4 upon 5 raised to 4. This works out to be 0.24576. In the second problem, we have to find the probability when at least 2 bombs will hit the target. So P x equals at least 2 will be 1 minus P x equals 1, which is 1 minus 6c1 1 upon 5 4 upon 5 raised to 5, which equals 1 minus 0.3932, which is 0.6068. So the probability that 2 bombs will hit the target is 0.24576, and the probability that at least 2 bombs will hit the target is 0.6068. There are 800 families, which means capital N is 800, and each family has 5 children, means small n is 5. In the first question, we have to find how many families we can expect to have 3 boys. So probability of a boy, say P, is half, and probability of having a girl is Q, which is 1 minus half, half again. Now probability of 3 boys in a family will be 563 half cube into half square. 5c3 is 5c2, 5 into 4 upon 2 into 1 upon 8 into 1 upon 4, which is 5 upon 16. So the number of families having 3 boys out of 5 children will be 800 multiplied by 5 upon 16, 250 families. In the second question, we have to find how many families will have 5 girls. It is P x equals 5, 5c 5, half raised to 5, half raised to 0. 5c5 is 1, half raised to 5 is 1 upon 32. So the number of families with 5 girls out of 5 children will be 800 into 1 upon 32, 25 such families. Here small n is 6, capital N is 729. Probability of getting 5 or 6 will be P of x equals 5 or 6. Probability of getting 5 is 1 upon 6 and that of getting 6 is 1 upon 6, which is 2 upon 6, 1 upon 3. Therefore P is 1 upon 3. Q will be 1 minus 1 upon 3, 2 upon 3. We have to find the probability of getting at least 3 dice, 5 or 6. So we write P of x equals at least 3 dice to show 5 or 6, which will be 1 minus probability when x is 0 plus probability when x is 1 plus probability when x is 2. Probability when x is 0 is 6c0, 1/3 raised to 0, 2/3 raised to 6, 1 into 1 into 0.0878. Probability when x is 1 is 6c1 into 1 upon 3 into 2 upon 3 raised to 5, 6 into 1 upon 3 into 0.1317, which is 0.2634. Probability when x is 2, 6c2, 1 upon 3 squared, 2 upon 3 raised to 4, which is into 0.1975, which is 0.3292. Addition of these three quantities, so this will be 1 minus 0.6805, which is 0.3195. And the expected number of times this will happen will be 729 multiplied by 0.3195, approximately 233 times. If you like this video, please like it, share it and subscribe to this channel. See you in the next video. Until then, keep watching Number Collage. Thank you.